Carbonyl compounds are going to be those that contain a carbonyl group, like aldehydes and ketones. Aldehydes and ketones contain this carbon double bonded to an oxygen. Aldehydes are always terminal, and ketones are internal. That's the major difference about where they're located. They do have different properties, but both are found in various naturally occurring compounds. They're intermediates in metabolism and our synthesis of biological compounds. They're also very common chemicals, like for solvents, monomers, those that make up our polymers, adhesives, agrochemicals, and pharmaceuticals. So we will see these quite a lot in nature and in industry. So contain that carbonyl group. So here's the carbonyl group. This is an aldehyde. Now here the R group can be hydrogen. It can be an alkyl group or an aromatic compound. Well, an aromatic group, I should say. When we write it condensed like this. Why do we write it like that? We went over that in our intro chapter because if I were to write RCOH, it would look like an alcohol. So we don't want to write it like that. So we write RCHO. Methanol, which is formaldehyde, is the simplest one, and that would be where this is a hydrogen. So that would be methanol, which is formaldehyde. This is our ketone. So we have two R groups here. And the R group can be alkyl or it can be aryl, but it can't be hydrogen. When you write it condensed, you can write it just like this with the oxygen in the middle between the two R groups in that carbon, and we will know it's a carbonyl because of how many bonds there are to that particular carbon. So the carbonyl group is going to bring up some special properties because it's very polar. The carbonyl group can't form hydrogen bonds with itself, but it does have a dipole here that is going to make our dipole-dipole interactions, but it means it can hydrogen bond. It can accept hydrogen bonds from water, so we can see that it's going to be more soluble in water than it would be otherwise. So this would be a hydrogen bond that it's accepting from water. It doesn't have a hydrogen bonded to the oxygen by itself, so it can't hydrogen bond with itself, but it can accept those hydrogen bonds from water. And when it does that, it becomes more soluble. So carbonyl compounds with up to 4 carbons are pretty soluble in water, and then we start to see the solubility drastically decline up to 5 and 6 carbons. So this is our hydrogen bond. Remember that this is an attraction. This is why we draw a dotted line rather than a solid line. This is just a picture showing our carbonyl group. So this is our carbonyl group here, forming those hydrogen bond attractions to water, where it's accepting those hydrogen bonds from water. But oxygen can also have an attraction here from the water to the partially positive carbonyl. That's a dipole. So this is our dipole-dipole. Not the special hydrogen bonding one, but this is the special hydrogen bonding dipole. Intermolecular force there. So we can see that it's going to cause greater solubility. That's an R. Now, this ability is actually going to cause higher melting points and boiling points. So this is going to be something we're going to talk about in a minute. It's a special way that it can actually, if you see how good it fits in here with this one going up and these ones coming down here like this. Some of these fit really well together and attract each other in so many ways. They form even stronger, more attractive forces than we would expect, making their boiling points and melting points even higher. But all these intermolecular forces here, even though they're dipole-dipole, are going to cause the melting points and boiling points to increase. So what have we talked about so far? These are going to be medium boiling points from what we've talked about so far. Ethers, alkanes. Al is a aldehyde, CHO. One is a ketone. Here's our ketone. All alcohol. And this one we haven't discussed quite yet, but this is a carboxylic acid. All right, so let's take a look at the boiling points. Remember these ethers, they have that oxygen buried in the middle, even though they are polar. They don't have necessarily access to be having the ability to having the ability to reach each other as well. So their boiling points and their as compared to their molecular weights. Well, I'm tripping over my words. I'm sorry. So their boiling points are going to be a little bit less, but as compared to an alkane, they're pretty similar, even though they have that polar oxygen group in there. Now, butanol, aldehydes, and ketones are going to be pretty similar to each other in their boiling points and melting points. I'm not going to ask you to put them in order when they have each other. I will ask you to say, where do they fall in the chain of things that we've discussed so far? So as compared to an alcohol, they're going to be lower, and as compared to a carboxylic acid, they're going to be much lower. So they're somewhere in the middle right now. They're less soluble in water as the hydrocarbon increases, just because we're adding all those nonpolar forces in there. And then we can't really overcome that. So about 4 carbons per aldehyde or ketone group is going to be more soluble. Now, formaldehyde, remember our simplest, this wouldn't be a bad structure to know. I didn't mean to draw a line through that. I think that was an accident on the computer. So this wouldn't be a bad structure to know. This is formaldehyde. It's pretty common. So this is going to be infinitely soluble. It's small, and it has that, it's basically just a carbonyl compound, so it's going to be infinitely soluble. But also acetaldehyde and acetone are going to be infinitely soluble as well. And I'll draw those. I don't have much room right now, so I'll draw those in a little bit. But first, let's learn how to name these. So remember, we're going to follow all the same naming rules that we've been following. We're just going to change the ending to something else now. And the aldehyde is going to take precedence. So we're going to find the longest chain that includes the carbonyl group. If it's an aldehyde, it's always going to be on the end, where we're going to place the E of alkane name with al, and the aldehyde carbon is always number 1, so you don't have to number it in this case. So 1, 2, 3, 4, 5. We have a methyl group here. So 4-methyl, right? It's 5 carbons, so it's pentane, pentanal. So pentanal, we don't need a number. We have a methyl at number 4. So 4-methyl pentanal. Here we have an aldehyde, but we also have an alkene. We have an ene functional group. When we have another functional group here, like an alkene, so we're going to go over a couple different functional groups, but when we have an alkene or an alkyne, the aldehyde is going to take precedence. Remember, it's always going to be at carbon number 1, so it's going to take precedence there. So we have to say whether this is cis or trans. And we can see that these hydrogens are facing on the same side. Find a similar group, that's where we're extending that definition. Find a similar group if they're on the same side, that's cis, and if they're on opposite sides, it's trans. Yes, you can use the hydrogens to determine that in this case. Remember, that's a stretch of our definition, so we don't have to go into E and Z nomenclature. All right, so we have cis or trans for the alkene. We're going to have to say what number it's at. 1, 2, 3, 4, 5, 6. So we're going to have 4-ene, and we're going to have the al at the end. So this is hexane. We drop the ane, hexene, right? Hexene. We have to put that ene in there. We're going to have to number that ene, but we'll do that in a second. And then we have the al saying that's an aldehyde. So the ene is at number 4. Then we have to say cis. So we have cis for hexene al. So this 4 goes to the ene. The al is always number 1. You can also write it with the 4 in the middle to say that specifically this 4 goes to the ene if you want to be more clear. Just doesn't roll off the tongue as nice. So aldehydes are also going to take priority over an alcohol. The alcohol is going to be named a hydroxy group when it's named as a substituent. 1, 2, 3, 4, 5. We have a pentane, Pentane becomes pentanal. And now we need to put the hydroxy group in there, which is at number 5. So 5-hydroxypentanal. Now the aldehyde's also going to take priority over an amine group. So here we have an amine, which is called an amino. Amino group when it's a substituent. So we're going to number this 1, 2, 3, 4, 5. This is going to be pentane, becomes pentanal. Oops, go back. Okay, so this was pentane, pent, and al. I have an amino group at number 4, so 4-amino pentanal. IUPAC does retain the use of some of our well-known unsystematic names for a few ketones. This is acetone. I said I was going to draw it out, but it's here. I don't have to draw it out for you. So what would that look like in a line structure? It would look like this. This is acetone. Acetone, I'm having a hard time today. Acetone is an excellent solvent for organic compounds, but it eats just about everything. So you don't want to put it on plastic or anything like that because it'll eat that. But if you want to clean your glassware, you want to remove any writing off of it, that'll definitely work and it'll get it done, fast, and in a hurry. This is acetophenone. So we have our phenyl group here, and we have our, what is this? It's a ketone because this is not a hydrogen, right? So acetophenone, ending in -one, tells me it's a ketone. Benzophenone, I have a benzene group on either side of the ketone. So these are a few that we probably should know because they're going to be retained by the IUPAC system. Now, if we have an aldehyde connected to a ring, the aldehyde carbon is not part of the ring. It can't be because aldehydes have to be terminal. So there's the method of doing this is you're going to actually name the ring. So this would be cyclopentane, and then you write carboxaldehyde or carbaldehyde actually. I've done both, but we'll go with carbaldehyde. So then you just push them together. So cyclopentane, carbaldehyde. There you go. Rolls right off the tongue, doesn't it? So that's just basically naming the ring as a substituent, but we don't change the ending like it's a substituent. So you just name them both and put them together. I want you to pause this and practice. So name these. If it is one of the ones that has a common name that's retained, you can use that. If you don't pause it, you're just missing out on the practice. So I would pause it, but I'm not going to because, well, I got to give you the answers. So this is meth and al. It would be methane, but now it's methanal. This would be, now we have 2 carbons, eth, al. Okay, I'm not sure what's going on there, but I think I'm going to just rewrite that one. All right, now the next one we might have to actually count. These are pretty simple ones here. 1, 2, 3, 4, 5. This would be pentane, but we drop the E and add al, pentanal. All right, these ones are going to have some substituents. 1, 2, 3, 4, 5. So at number 2, we have a chloro group. So 2-chloro, pentanal. All right, here we have 1, 2, 3, 4. It would be butanal. And here we have 1, 2, 3, 4. We have a methyl group here. This would be 3-methyl butanal. right, so how'd you do? All right, we're going to discuss common names here for a moment, but that's our IUPAC naming system. Oh, well, I guess I did have those in there, so there you go. I want to take a look here at something. Valoraldehyde, formaldehyde, acetaldehyde, valoraldehyde, alpha chlorovaloraldehyde. So this is our carbonyl compound. This is alpha, beta, gamma. Butyraldehyde, because it comes from butyric acid. Isovaloraldehyde. These are the common names. So sometimes you might get angry at the IUPAC system, but common naming for aldehydes is just so. Like this is our one from the previous slide. We have 1, 2, 3, 4, 5 carbons, and we have this chloral group. So you use Greek letters to indicate the position. So this would be our carbonyl compound, alpha, beta, gamma, gamma chlorovaloraldehyde. Why does it come from valoraldehyde? Because that's what we name the one that has 5 carbons. And you would just have had to memorize all of those. So you will not be responsible for this. You're not going to have to be tested on these common names except for formaldehyde, and acetaldehyde perhaps would be on there, but nothing more than that. I try to use the IUPAC naming system, but those are ones that you might come in contact with more often. But after that, we've replaced it with the IUPAC system. So as much as you might get annoyed with the IUPAC system, be thankful you don't have to do that anymore. How do we name ketones? Very similarly, except for now it's going to be internal and not terminal. So a ketone can never be 1, right? Okay, so keep that in mind. Now the parent alkane is still the longest chain that contains the carbonyl. We replace the E of the alkane name with -one, and then we numbered a chain to give the -one the smallest possible number. It cannot be number 1 because then it's called an aldehyde. So 1, 2, 3, 4, 5. So we have the carbonyl at number 2. This was a pentane, but now it's a pentanone. We have to put a number for where that -one is. So we're going to say 2-pentanone, and we have a chloro group at number 4. So 4-chloro, 2-pentanone. Alternatively, the 2 can also go here. So we can say 4-chloro-pentan-2-one. Ketones in rings are actually part of the ring, so it's a little bit easier than we had them with carbonyls. It's more straightforward. The carbonyl is always going to be number 1, so this will be cyclohexane -one. So cyclohexanone, we just replace the E with the -one. Ketones do take priority over alkenes and alkynes, so this is going to take priority. So we'll say 1, 2, 3, 4, 5, 6 rather than 1, 2, because even though this has a smaller number, it takes priority. So we're going to have that ketone group taking priority. So ketone is at number 3, the alkyne is at number 4. And here we go. So 1, 2, 3. We have hex, -ine. You know, I think there's a typo in this slide on this one I forgot to do. So we're going to go back and I'll just write it. So this is hex. It was hex-ine. And we have the -one at number 1, 2, 3. So hex-ine, 3-one. We have our alkyne at number 4. 4-hexyne 3-one. Alternatively, you can say hex 4-yne 3-one. Oh, I did fix it. Okay, so there we go. Ketones take priority over alcohol groups. The alcohol becomes a hydroxy group. So we're going to say 1, 2, 3, 4, 5, 6. Remember, before we would have said this is number 1, but not anymore because this group takes priority. So now we have a hexane. It was a hexanol before, but now we're going to change that to an one. So we're going to say hexan one, and we'll name the substituent hydroxy. So we're going to say hexan one. The one is at number 2, and we have a hydroxy group at number 6. Alternatively, you can say 6-hydroxy hexan 2-one. Oops, go back. There you go. All right, ketones take priority over amines. So here's an amine group here, but the ketone is going to be taking precedence over that. So when we name the ending, it'll be an one. We have to say 1, 2, 3, 4, 5, 6. I guess I need to fix that, but we have our one at number 2. We have an ethyl substituent here at number 4. And we have the amino at number 3. So 3-amino, 4-ethyl, 2-hexanone. Aldehydes take priority over ketones. So if we have them in the same molecule, the aldehyde's going to take precedence because it's always number 1. So 1, 2, 3, 4, 5. We're going to say pentanal. We don't need a number for the aldehyde because it's always number 1. We're going to actually call that ketone group, we're going to call it an oxo group. So it'll be 4-oxo pentanal. Naming ketones in a common way, instead of IUPAC, you name each alkyl group or aromatic group that's bonded to the carbonyl carbon as a separate word, and then you follow it by the word ketone. This is still very, very popular, so you might actually see this. Now, this is an aldehyde. This is a carboxylic acid. These are ketones. So I just wanted to give you a little bit of a thing there just to make sure that you're paying attention. All right, so that's acetaldehyde. This is acetic acid. Now here we have a methyl, and we have 1, 2, and ethyl. So this would be methyl ethyl ketone. This is also known as MEK in industry, so they get even shorter, and we do definitely use these in industry. So here we have ethyl and isopropyl. So ethyl isopropyl ketone. Alphabetical order is also, again, the way to do this. I would highly recommend doing this with alphabetical order because it's always acceptable. Whereas some of these are allowed to go in increasing size, and this is one of them. But since alphabetical order is always an accepted way to do that, I don't see why you would fill your brain with which ones are and which ones are not allowed to do increasing size order. But in this case, ethyl isopropyl ketone is what this one would be named. So, all right, moving on. Let's see what they do in nature. We said they're very popular in nature. Where are they? So methanol, again, formaldehyde, has a boiling point of negative 21 degrees Celsius, is used. We put it into aqueous solutions called formalin. This is the stuff that you smell when you're doing dissections and other things, but it is a tissue preservative. So we can also use that to embalm bodies. Acetone and methyl ethyl ketone, MEK, are versatile solvents. We use them all over the place. I used to use one, MIBK, all the time. In fact, I got that in my eye one time. I had to use the eye wash. 15 minutes is a long time. They're very popular flavorings or scents. So vanillin is vanilla beans, our smell and flavor. You can see we have an aldehyde here. We also have an ether and an alcohol. So those are some functional groups. 2-octanone. So this is our ketone group here. This is mushroom flavor. Yum. I don't know. Maybe you don't like fungi. Sorry. All right. Benzaldehyde. This is the one I was mentioning to you the other day in class that if you're allergic to almonds, you will also react to benzaldehyde. So this has almond scent flavor. Cinnamaldehyde is cinnamon, and that's what it looks like. Then we also have lemongrass. This is called citral. If you look at that, got a aldehyde here, right there. And here we have a ketone in this one. This is berry flavoring, alpha demescone. Yeah, tomato. All right, that's some useful type of compounds. We're going to end here, and then we're going to start talking about reactions in the next video.